there is something profoundly deceptive about the way we perceive the universe. We seem to move through space, traversing distances, while time flows inexorably around us like an invisible river. Space here, time there, two distinct, separate, independent things. But this separation is an illusion, a trick of our limited senses. The truth is far more elegant and surprising. Space and time are not separate entities. They are fundamentally intertwined, fused into a single unified structure that permeates all of existence. We call this structure space-time. This revolutionary revelation did not come from direct observations or simple experiments. It came from the brilliant mind of Albert Einstein at the beginning of the 20th century when he developed his theory of relativity. Einstein realized something that no one before had fully understood: that space is not just an empty stage where events happen, and time is not just a universal clock ticking uniformly. Instead, they are interconnected aspects of something more fundamental, something that can be bent, stretched, distorted by the presence of mass and energy. And this realization completely changed our understanding of gravity. For centuries, since Newton, we thought of gravity as a force. Massive objects pulling other objects through the void of space. But Einstein showed us a deeper truth. Massive objects don't pull. Instead, they curve the very fabric of space-time around them. It's like placing a bowling ball on a stretched trampoline. The fabric deforms, creating a depression, a curvature in the surface. And it is this curvature that we call gravity. Gravity is not a mysterious force acting at a distance. It is simply the geometric consequence of living in a curved space-time. Objects move through this curved structure in the most natural way possible, following what we call geodesics, the straightest possible paths through a space that is not flat. Think of planets orbiting stars. They aren't being pulled by invisible strings. They are simply following natural curves in space-time created by the star's mass. It's like a marble rolling around the depression created by that bowling ball on a trampoline. The marble isn't being pulled. It's following the curved geometry of the surface. Similarly, the Earth orbits the Sun not because it's being pulled, but because it's following a curve in space-time that the Sun created simply by existing. And the magnitude of this curvature depends directly on the amount of mass present. The greater the mass, the deeper the depression in the fabric of space-time, the more extreme the curvature. A star curves space-time more than a planet. A black hole curves it more than a star. It's a direct and elegant relationship. More mass means more curvature, and more curvature means stronger gravitational effects. Our own sun, that incandescent ball of plasma at the center of the solar system, curves space-time around it into a subtle but significant depression. And it is this curvature that keeps Earth in its nearly circular orbit, neither falling toward the sun nor escaping into interstellar space. We are perpetually falling through curved space-time, but our lateral velocity transforms this fall into a closed circle, a stable orbit. But there are places in the universe where the curvature of space-time becomes so extreme, so intense, that the very structure of space and time is radically distorted. These places are black holes, regions where so much mass has been compressed into such a small volume that space-time is curved beyond any reasonable limit. Near a black hole, the geometry of space-time becomes so distorted that not even light can escape. It's as if the fabric were pulled down into an infinitely deep well. And in these regions of extreme curvature, something extraordinary happens to time. It slows down. Not subjectively, not metaphorically, but literally, measurably. A clock near a black hole would tick slower than a distant clock. An observer near the black hole would experience time passing normally, but when compared to someone far away, they would find that much less time has passed for them. This phenomenon has a name: time dilation. And time dilation is not just an abstract theory or a mathematical curiosity. It's real, measurable, and we have to deal with its consequences in our everyday technology. Clocks on GPS satellites orbiting Earth keep time slightly differently than clocks on the surface. This happens for two reasons related to space-time. First, the satellites are moving rapidly relative to the surface, and second, they are in a region where Earth's gravitational field is slightly weaker, where space-time is a little less curved. The GPS system only works accurately because the engineers who designed it included corrections for these relativistic effects. Without taking into account time dilation caused by both orbital speed and the difference in the curvature of space-time, the positions calculated by GPS would deviate by several kilometers per day. It's a daily confirmation of the reality of curved space-time. Every time your smartphone tells you where you are, it's using calculations that take into account Einstein's theory of relativity. And it's not just gravity that affects time. Traveling very fast does too. The closer you move to the speed of light, the slower time flows for you compared to stationary observers. It's another aspect of relativity. Speed and gravity both distort space-time in ways that affect the passage of time. The closer you travel to the speed of light, the more dramatic the effect. At ordinary speeds, walking, driving, even in supersonic planes, the effect is too minuscule to be noticed without extremely precise instruments. But as you approach that fundamental speed of the universe, time for you begins to crawl compared to the rest of the universe. And at the extreme limit, traveling at exactly the speed of light, something extraordinary happens. For a photon, a particle of light, traveling at this maximum speed, time practically stands still. From the photon's point of view, its journey is instantaneous. It is emitted from an atom in a distant star, and, from its own subjective point of view, reaches its eye at the same instant, even if trillions of kilometers and thousands of years have passed from our point of view. For light, birth and arrival are simultaneous. But space-time isn't just curved. It can also stretch. The very fabric of space-time is expanding, and this expansion is happening now, constantly in all directions. The expansion of the universe, that phenomenon we discovered in the 20th century when we observed distant galaxies moving away from us, isn't simply objects moving through space. It's something far more fundamental. It's the expansion of space-time itself. Distant galaxies aren't flying through space away from us like fireworks scattering after an explosion. Instead, the space between us and them is literally expanding. It's like drawing dots on a balloon and then inflating it. The dots move away from each other not because they're moving across the surface of the balloon, but because the surface itself is expanding. Galaxies are essentially stationary in their own local space, but space itself is stretching between them. And this expansion has no center. There is no special point in the universe from which everything is moving away. Instead, space-time is expanding in all directions simultaneously. Every point in the universe sees all other distant galaxies moving away, and each galaxy can consider itself the center of this expansion from its own perspective. It is a uniform expansion of the very structure of space, with no central origin, no edge. Breathe gently. Visualize this invisible fabric connecting everything, curving around masses, stretching across the cosmos. There is so much more to discover about the nature of space-time. It is crucial to understand something that challenges our everyday intuition. Space-time is not a passive stage, a neutral backdrop where the universe simply unfolds its events. It is an active, dynamic participant, responding to the presence of mass and energy, influencing the movement of everything that exists. It is as if the stage itself were alive, bending and flexing in response to the actors, and in turn, directing how those actors move. And the relationship between mass and curvature is direct and proportional. The greater the mass of an object, the more deeply it bends space-time around it. A rock creates a tiny, almost imperceptible depression. A planet creates a significant depression. A star creates a substantial distortion. And even more massive objects create increasingly dramatic curvatures, distorting the fabric of space-time in ever more extreme ways. This curvature is not a metaphor or a convenient analogy. It is literally what we feel as gravity. When you feel your weight, when you feel the earth pulling you down, you are not experiencing some mysterious force acting at a distance. You are experiencing the consequence of living in a space-time curved by the mass of the earth. Your feet are trying to follow a geodesic, the straightest possible path through curved space-time, and that natural path happens to point toward the center of the Earth. The Earth orbits the Sun because it is following the curvature that the Sun created in space-time. It's like a ball rolling around a funnel. There are no strings, no pulling force. Just geometry, pure and simple. The Sun's mass deforms space-time, creating a depression, and the Earth follows the curvature of that depression, moving in a trajectory that we see as a circular orbit. But here's something fascinating to consider. If the Sun were to disappear instantly, simply cease to exist, evaporate in the blink of an eye, the Earth wouldn't feel the effect immediately. We would continue orbiting normally for exactly 8 minutes. Only after those 8 minutes would we realize that something had changed, and our orbit would begin to transform into a straight line, sending us adrift through interstellar space. This 8-minute delay is not arbitrary. It occurs because changes in space-time, changes in curvature, do not propagate instantaneously. They travel at the speed of light. When the Sun disappeared, the alteration in the curvature of space-time, the sudden flattening of the depression that the Sun created, would spread outward as a wave, moving at 300,000 kilometers per second. And it would take exactly 8 minutes for this wave to reach Earth, the same amount of time that light takes to travel from the Sun to us. Black holes represent the absolute extreme of this curvature. They are regions where so much mass has been compressed into such a small volume that space-time is curved beyond any reasonable limit. The curvature becomes so extreme that it creates an event horizon, a one-way boundary through which nothing, not even light, can escape. And within this horizon, the very structure of space-time is so distorted that the mathematical equations that describe it suggest something extraordinary. Space and time can literally switch roles. In our normal experience, we can move freely through space, forward, backward, left, right. But we are inexorably dragged through time in a single direction. But inside a black hole, the equations suggest that this distinction is reversed in certain ways. It's a concept that defies visualization, bordering on the incomprehensible, but it's what the rigorous mathematics of general relativity indicates. Near a black hole, even before crossing the event horizon, time dilation becomes dramatic. An observer hovering near the event horizon would experience time passing normally for them. But if they looked into the distant universe, they would see events unfolding at accelerated speed. Conversely, a distant observer looking at someone near the black hole would see that person moving in super slow motion, their clocks ticking slower and slower as they approached the horizon. And these aren't just theoretical thought experiments. We measured time dilation directly using atomic clocks, the most precise time-measuring devices humanity has ever created. We placed identical atomic clocks on satellites and on the Earth's surface, and when we compared their readings after some time, we found that the clocks in orbit ran slightly faster than the clocks on the surface. The difference is minuscule, mere fractions of a second over years, but it's real, measurable, and corresponds exactly to the predictions of relativity. The GPS system, the one we use daily for navigation, must account for these effects with extreme precision. Without relativistic corrections compensating for both the time dilation caused by weaker gravity in orbit and the effects of orbital velocity, the positions calculated by GPS would deviate by kilometers per day. It is everyday proof that space-time is not just an elegant mathematical abstraction, but a physical reality that influences even the most practical and mundane technologies. And space-time can do something even more extraordinary. It can vibrate. Just as the surface of a lake can ripple when disturbed, the fabric of space-time can sustain waves. Literal ripples in the geometry of space and time, traveling through the cosmos at the speed of light. We call these ripples gravitational waves. Einstein predicted the existence of these waves in 1916 as a natural consequence of his equations of general relativity. If space-time can be curved, and if changes in this curvature propagate at finite speeds, then violent perturbations should create waves that spread outward, carrying energy throughout the universe. But for decades, they remained only theoretical predictions, impossible to detect with available technology. It was only in 2015, almost a century after Einstein's prediction, that gravitational waves were directly detected for the first time. The LIGO detectors, incredibly sensitive laser interferometers capable of measuring distances smaller than the diameter of a proton, captured the unmistakable signal of two gravitational waves generated by a cataclysmic event. The collision and merger of two black holes orbiting each other millions of light years away. These waves arise when massive objects collide or orbit each other in extreme configurations. Two black holes spiraling toward each other. Two neutron stars colliding. Even the Big Bang itself must have generated primordial gravitational waves still reverberating through the cosmos. Each violent and massive event sends ripples through the fabric of space-time, like waves on a cosmic lake. And gravitational waves carry information about events that would be completely invisible to light. Colliding black holes don't emit light. They are, by definition, dark. But they scream in gravitational waves, dramatically distorting space-time around them as they merge. It's a new form of astronomy, a new sense we've developed for observing the universe, not with light, but by listening to the vibrations in the very fabric of space-time. And these waves traverse the universe almost unaffected by matter. Light can be blocked by clouds, absorbed by dust, deflected by gravitational lenses. But gravitational waves pass through everything. Planets, stars, galaxies, almost as if they weren't there. They carry pristine information from their points of origin, uncorrupted by the journey, offering a clear window into events that would otherwise remain hidden. And let's return to that expansion we mentioned earlier. Space-time can be stretched, and is being stretched now, everywhere, constantly. The expansion of the universe isn't galaxies flying through pre-existing space. It's space-time itself that is expanding, growing, creating more space between distant objects. Distant galaxies aren't moving through space in any conventional sense. They're essentially stationary in their own local space. But the space-time between us and them is stretching, creating more distance, making them appear to recede. It's like dots drawn on a stretched elastic band. The dots don't move along the band, but the distance between them increases as the band itself expands. To truly understand space-time, we need to abandon the idea that it is something rigid, fixed, and immutable. Space-time is not like an inflexible steel grid. It is more like an elastic, flexible, responsive fabric, capable of being bent, stretched, compressed, and undulating. It is a dynamic medium that responds to the presence of mass and energy, deforming in ways that determine how objects move through it. The greater the mass of an object, the deeper it sinks into this elastic fabric. A small mass creates an almost imperceptible depression. A large mass creates a deep pit. And it is this sinking, this curvature, this geometric deformation that we perceive and experience as gravity. It is not a force in the traditional sense, no invisible string, no ghostly hand-pulling. It is simply geometry, the shape of space-time itself. And when we see planets orbiting stars, we should visualize not spheres being pulled by invisible forces, but objects naturally following the curves of space-time. It's like marbles rolling around depressions in a flexible surface. The star creates the depression, and the planets simply follow the contours of that depression, tracing orbits that are, from the point of view of local geometry, the straightest possible paths. And let's return to that fascinating thought experiment. If the sun were to disappear instantly right now, at this very moment, the Earth wouldn't react immediately. We would continue orbiting exactly as we always have for approximately 8 minutes. During those 8 minutes, we would be completely unaware that the sun had disappeared. We would still see its light. The photons emitted 8 minutes ago would still be arriving. We would still feel its gravity. The curvature of space-time that it created would still be present locally. Only after those crucial 8 minutes would the information about the sun's disappearance finally reach us. The light would suddenly go out, and simultaneously, the gravitational curvature of space-time would smooth out, the depression would disappear, and our orbit would become a straight line. That is the time it takes for gravitational information, changes in the curvature of space-time, to travel to us from the sun. Because there is a fundamental cosmic speed limit. Nothing in the universe can transmit information faster than light. Not even gravity. Changes in the gravitational field, alterations in the curvature of space-time, propagate at exactly the speed of light, neither faster nor slower. It is a fundamental limit embedded in the very fabric of space-time. And these gravitational waves we mentioned, those vibrations in the fabric of space-time, are real physical manifestations of this finite propagation of gravitational information. When massive objects collide or orbit in extreme configurations, they create ripples that spread through space-time, carrying energy and information at the speed of light. Einstein predicted these waves in 1916 as an almost inevitable consequence of his equations. If space-time can be curved, and if changes in that curvature propagate at finite speeds, then violent events should create waves. But for almost a century, they remained only theoretical predictions. The technology needed to detect them simply did not exist. The waves are extraordinarily weak when they reach Earth, stretching and compressing space in amounts smaller than the diameter of a proton. Only in 2015, with the LIGO detectors operating at the absolute limit of measurement precision, were gravitational waves finally detected directly. It was a triumph of engineering, of scientific persistence, and an extraordinary confirmation of Einstein's vision of the nature of gravity and space-time. These waves arise when extremely massive objects collide or move in asymmetrical and violent configurations. Two black holes spiraling toward each other, accelerating as they approach, finally merging in a cataclysmic collision that releases more energy and gravitational waves than all the stars in all visible galaxies emit as light at that same moment. It is a release of energy so vast that it defies comprehension. When black holes merge, space-time literally trembles, like the surface of a lake disturbed by a giant rock. These ripples spread outward in all directions, stretching and compressing the fabric of space-time as they pass. And these tremors traverse entire galaxies, traveling millions or billions of light years, almost without losing energy. They pass through stars, planets, gas clouds, passing through almost everything as if it weren't there. And space-time isn't just locally flexible. It can stretch and contract on cosmic scales. This happens naturally, constantly, throughout the universe as it expands. The expansion of the universe, that phenomenon first observed by Edwin Hubble in the early 20th century, isn't simply objects moving. It's the expansion of space-time itself, the fundamental fabric of reality growing, creating more space between distant objects. Galaxies aren't moving through space in any conventional sense. They are essentially stationary in their own local frame of reference. But the space between them is growing, expanding, creating more distance. It's as if the universe were a balloon being inflated, with galaxies as dots painted on its surface. The dots don't move across the surface of the balloon, but as the balloon expands, the distance between them increases. And there's a fascinating consequence of this expansion. The farther a galaxy is from us, the faster it appears to be moving away. This happens because there's more space between us and distant galaxies, and all of that space is expanding simultaneously. It's a cumulative effect. The more space there is between us and an object, the faster the apparent rate of recession. And at extreme distances, this accumulated expansion can make galaxies appear to be moving away from us faster than the speed of light. This seems to violate that cosmic speed limit we mentioned, but it doesn't actually. The limit applies to movement through space. No object can travel through local space faster than light, but there is no limit to how fast space itself can expand. Space-time can grow at any rate, and sufficiently distant objects can move away from us seemingly faster than light simply because the space between us and them is expanding so rapidly. And, on truly cosmic scales, space-time defines not only the present, but the ultimate destiny of everything that exists. If the expansion continues to accelerate, and all current observations suggest that it will, then the distant future of the universe will be determined by this expansion of space-time. Galaxies will move further and further away, until eventually, billions of years in the future, observers in our galaxy will no longer be able to see any other galaxies. The observable universe will shrink, not because space is shrinking, but because the expansion will have pushed everything beyond our cosmological horizon. Take a deep breath. Feel the universe gently expanding around you. Visualize this elastic fabric vibrating, stretching, defining the destiny of galaxies. There are still more revelations waiting about the nature of time and space. It is crucial to understand that space-time is not merely a passive stage, a neutral backdrop where cosmic drama unfolds. It is an active participant, a dynamic player that fundamentally shapes how events happen. Without space-time and its peculiar properties, its ability to be curved, to respond to mass, to propagate change at finite speeds, the universe as we know it simply could not exist. Without space-time, there would be no stable orbits. Planets would not circle stars. Moons would not orbit planets. Stars would not cluster into organized galaxies, majestic spirals, or massive ellipticals. The very large-scale structure of the universe, that cosmic web of galactic filaments separated by voids, is a direct consequence of how matter interacts with space-time, how it curves it, and how that curvature, in turn, directs the movement of more matter. Every object with mass, no matter how small, creates a permanent mark on the fabric of space-time. Your own body, sitting or lying down right now, is curving space-time around you. The curvature is minuscule, imperceptible without extremely sensitive instruments, but it exists. Every atom, every particle, every photon of light, all leave their imprint on the geometry of space-time. And the more massive the object, the deeper and more extensive this deformation. A rock creates a microscopic depression. A planet creates a significant depression that extends for thousands of kilometers. A star creates a deformation that extends for billions of kilometers. A black hole creates such an extreme distortion that space-time literally folds back on itself. This is the fundamental reason why planets follow curved trajectories instead of straight lines. In the absence of curvature, in the absence of any mass to deform space-time, a moving object would continue in a straight line forever. But in the presence of curvature, the very concept of a straight line changes. The straightest possible trajectory through curved space is itself curved when viewed from an external perspective. It is pure geometry dictating movement. And it's not just matter that responds to this curvature. Even light, which is massless and traveling at the maximum speed in the universe, follows these curves when it passes near large masses. Rays of light traveling through deep space, which would otherwise continue in perfectly straight lines, are deflected, bent, when they pass near massive stars, galaxy clusters, or black holes. This effect has a name: gravitational lensing. It's as if massive objects act like giant lenses, bending the light that passes through the curved region of space-time around them. And this effect isn't just a theoretical curiosity. It's a powerful tool that astronomers use regularly. Thanks to gravitational lensing, we can see galaxies that are literally behind others from our point of view. The light from these distant galaxies, which would otherwise not reach our telescopes because it is blocked by closer galaxies, is bent around these intermediate galaxies. We see multiple images of the same distant galaxy, distorted into arcs or even complete rings, the so-called Einstein rings. It is space-time acting as a natural cosmic lens, magnifying and multiplying light from objects that would otherwise be invisible. And space-time grants us something truly extraordinary: the ability to see the distant past of the universe directly. because light travels at a finite speed, and because the universe is vast, looking far into space is literally looking back in time. When we observe a galaxy a billion light-years away, we are seeing it not as it is now, but as it was a billion years ago, when the light we are receiving began its journey through space-time. Some of the galaxies we observe today, especially the most distant and oldest ones, no longer exist in the form we see them. They have collided with other galaxies, merged, evolved beyond recognition. But their image, the photons emitted billions of years ago, is still traveling through space-time, finally reaching our telescopes now. It's like receiving postal letters from civilizations that may no longer exist. And space-time itself had a beginning. It didn't always exist. According to our best observations and models, space-time began with the Big Bang, approximately 13,800,000,000 years ago. At that initial moment, all of space, all of time, all of the energy and matter that would eventually form the observable universe were compressed into a state of unimaginable density and temperature. Before that, if before is even a meaningful concept, time itself may not have existed. It's difficult, perhaps impossible, to conceptualize a state where time doesn't exist. But the equations suggest that at the instant of the Big Bang, time began. There was no before in the conventional sense. Asking what happened before the Big Bang may be as meaningless as asking what lies north of the North Pole. There is no further north, because you've reached the limit of that direction. And since that initial moment, the universe has been expanding. But it's crucial to understand that this expansion isn't objects moving through pre-existing space. It's space-time itself that is expanding, growing, creating more space between objects. Galaxies aren't fleeing from each other through space. The space between them is literally growing, increasing in volume, pushing them further apart. And this expansion has a peculiar property. The farther away a galaxy is, the faster it appears to be moving away. This isn't because distant galaxies are moving faster. It's because there's more space between us and them, and all of that space is expanding simultaneously. It's a cumulative effect. Each tiny piece of space expands a little bit, but when you add up billions of light-years of space, all those small expansions accumulate into a huge rate of recession. On large scales, scales of hundreds of millions of light-years, space-time appears surprisingly homogeneous and uniform. Look at the universe on that scale, and you will see that the distribution of matter is relatively smooth. The geometry is relatively simple. It's like looking at an ocean from an airplane. The individual waves disappear, and you see only one smooth, uniform surface. But locally, on smaller scales, space-time is anything but smooth. It's full of curves created by stars, ripples generated by planets, extreme distortions around black holes. It's like approaching that ocean. Suddenly, you see individual waves, turbulence, complexity. And these local distortions shape absolutely everything. They determine how planets orbit. They direct how light travels. They influence how time flows for different observers. They even affect quantum processes at atomic scales. From the movement of the smallest atoms to the ultimate fate of entire galaxies, everything is shaped by the curves and distortions in the fabric of space-time. Imagine for a moment a hypothetical universe where space-time was completely flat, without any curvature, perfectly smooth at all scales. In this universe, there would be no gravity. Objects would float eternally in uniform motion, never being attracted to each other, never forming structures, without orbits, without planetary systems, without galaxies. It would be a cold, sterile cosmos, without form or organization, just scattered particles moving in straight lines through the void. But our universe is not like that. Gravity exists, and it exists precisely because masses curve the space-time around them. Every particle of matter, every quantum of energy, deforms the geometry of space and time. And the greater the mass concentrated in a region, the greater the curvature created. It is this curvature, this geometric deformation in the very structure of reality, that we manifest and experience as the apparent force of gravity. Planets don't orbit stars because they are pulled by mysterious forces. They orbit because they are following the most natural paths possible, geodesics, through a space-time that has been curved by the presence of the star. It is geometry dictating movement, structure determining trajectory. And at the absolute extremes of this curvature, we find black holes. These are regions where so much mass has been compressed into such a small volume that the curvature of space-time becomes pathologically extreme. The fabric doesn't just bend deeply, it essentially collapses in on itself, creating a singularity where the curvature approaches infinity. It's as if space-time develops a literal hole through itself, a region where the normal laws of physics break down. At the event horizon of a black hole, that one-way boundary through which nothing can escape, something extraordinary happens to time. To a distant observer watching something fall toward a black hole, time for the falling object appears to slow dramatically as it approaches the horizon. The object becomes increasingly redder due to time dilation. Its movements become increasingly slow, until, at the horizon itself, it appears to freeze completely. From the distant observer's point of view, the object never fully crosses the horizon. It is perpetually frozen at the exact moment before crossing it. But within the event horizon, the situation is even more bizarre. The equations of general relativity suggest that space and time literally switch roles mathematically. The spatial directions that can be freely chosen outside the horizon become fixed within it. And the temporal dimension, which flows inexorably in a direction outside the horizon, becomes something more like a spatial coordinate within. It's such a profound distortion in the structure of space-time that it defies visualization or intuition. As we explore ever smaller scales, approaching the minuscule distances where quantum effects dominate, space-time itself may cease to be the smooth, continuous structure it appears to be at larger scales. Some theories suggest that at scales on the order of the Planck length, approximately 10 to the power of minus 35 meters, space-time may be granular, discrete, composed of fundamental indivisible units. This idea suggests that there may be a fundamental minimum size, a scale below which the very concept of distance loses meaning. It would be like discovering that an apparently smooth fabric is, when examined with sufficient magnification, composed of interwoven individual threads. Space-time may have a fundamental structure that only reveals itself at these unimaginably small scales. And some modern theories go even further, proposing that space-time is not fundamental but emergent, that it arises from something even more basic. Just as temperature emerges from the collective movement of atoms, or as waves emerge from water molecules, space-time itself may emerge from more fundamental processes operating at a deeper level of reality. It is a profound and disturbing possibility that the stage itself may be an illusion, an emergent phenomenon from something more basic, yet not yet understood. Going back to the beginning of it all, the early universe had extremely compressed space-time. All the matter and energy in the observable universe, everything that would eventually become trillions of galaxies spread across billions of light-years, was compressed into a volume smaller than an atom. Space-time itself was curved to almost unimaginable extremes, with density and temperature reaching values that make the interior of stars seem cold and rarefied by comparison. And right after the Big Bang, something extraordinary happened. Space expanded faster than light. This period, called cosmic inflation, saw the universe increase exponentially in size in an infinitesimal fraction of a second. Regions that were causally connected were suddenly separated by distances so vast that light did not have time to travel between them. This doesn't violate physics. It doesn't break that cosmic speed limit we mentioned. Because it wasn't movement through space-time. It was the expansion of space-time itself. No object was moving faster than light through local space. Instead, the space between objects itself was expanding so rapidly that the distance was growing faster than light could travel through it. And this expansion never really stopped. Space-time continues to expand now, in all directions simultaneously. Every piece of space is growing, increasing in volume, pushing distant objects further and further away. It's a continuous, relentless process that defines the ultimate fate of the universe. Distant galaxies are not, in fact, moving away from us in any conventional sense. They are essentially stationary in their own local space. But the space between us and them is expanding, creating more distance, making them appear to recede. It is the universe's own metric that is changing, not the positions of the galaxies within that metric. On cosmic scales, time can have different rhythms, depending on the region of the universe. In regions of higher density, where the curvature of space-time is more pronounced, time flows slightly slower. In cosmic voids, where matter is rarefied and space-time is flatter, time flows slightly faster. The differences are minuscule, but real, measurable, and accumulate over billions of years. Looking to the distant future, trillions of years ahead, far beyond the lifespan of any currently existing star, the universe may be dominated by a cold, dark, and nearly empty space-time. Black holes will have evaporated through Hawking radiation. Stars will have burned all their fuel eons ago. Even protons may have decayed. What will remain will be mostly low-energy photons scattered throughout a perpetually expanding universe. Their light stretched to ever longer wavelengths by the continuous expansion. Even in this ultimate end scenario, sometimes called heat death, space-time will continue to exist, even with almost no energy. Even without organized structures, the very fabric of reality will persist, expanding eternally, cold and dark, but existing. And there is a poetic truth in this. Everything that has ever existed, every particle that has ever formed, every star that has ever shone, every thought that has ever crossed a conscious mind, has left a permanent mark on the fabric of space-time. The gravitational waves we generate, the tiny curvatures that our mass creates, propagate forever, attenuating but never disappearing completely, carrying information about our existence to the far reaches of the universe. Space-time is the invisible stage where the entire history of the universe unfolds. But it's more than a stage. It's an active participant, shaping events, determining destinies. And in a way, everything exists simultaneously within the four-dimensional structure of space-time. Past, present, and future all extended through this fundamental geometry, different points within a unified and eternal framework. Take one last deep breath. Let these ideas settle gently into your consciousness. Visualize space-time as an infinite cosmic tapestry, woven with the threads of space and time, curved by mass, vibrant with waves expanding eternally. Space-time is the most fundamental structure of the reality we know, the fabric upon which all existence is woven. Every moment you live, every breath you take, every thought you form happens within this extraordinary fabric, leaving its own tiny but permanent mark on the geometry of the universe. Good night. Sleep well. Dream of intertwined dimensions, of time flowing like thick honey near gigantic masses, of the entire universe vibrating gently like an infinite cosmic string.